So still under second order linear homogeneous differential equations, we are going to focus on fundamental sets of solutions and Wronskian. So let's consider a second order linear homogeneous differential equation, which is given of the form p of x times y prime prime plus q of x times y prime plus r of x times y equals 0. Now we already know that this is a second order linear homogeneous differential equation. Now assuming that we have y1 and y2 to be two solutions of the differential equation, and then c1 and c2 are said to be constants. Now, if y1 and y2 are linearly independent functions, okay, if y1 and y2 are linearly independent, then by the principle of superposition, what this primarily means is that the general solution of the differential equation is given by y equals c1 times y1 plus c2 times y2. Now, before we even get into what this thing is all about, let's try to understand linearly dependence and linearly independence. So, two functions are said to be linearly dependent if and only if one function is a constant multiple of the other. So let's assume that, for example, let's assume that we have a function y1 which is equal to x, and then we have another function y2 which is equal to 2x. Now looking at these two functions, you realize that y2 is a constant multiple of y1, which is y2 is equal to twice of y1. Now in this case, we say that the two functions y1 and y2 are linearly dependent because one is a constant multiple of the other. Now on the other hand, if you want to talk about linear independence, or two functions are said to be linearly independent if one is not a constant multiple of the other. If one is not a constant multiple of the other. Now, for example, we can talk about functions such as, let's say we have y1 equals cos x, and then we have y2 equals sin x. Now, these two functions are not linear dependent. They are linearly independent. That is, there is no way you can multiply cos x by any constants, be it 1, 2, 3, -1, and so on and so forth, to arrive at sin x. So y1 and then y2 here are linearly independent functions. So back to what we started with. Given a second order linear homogeneous differential equation, what we are trying to say is that if we have two solutions which are linearly independent, in the case y1 and then y2, and then we have c1 and c2 to be constants, then the general solution by the principle of superposition is given by y equals c1 times y1 plus c2 times y2. So let's assume that we are given a differential equation which is y prime prime plus y equals 0. This is the differential equation, the second order linear homogeneous differential equation. And then we are going to assume that y1 and then y2 are two solutions of the differential equation. So we have y1 to be cos x, and we have y2 also to be sin x. Now, based on these two solutions, we are going to find the general solution of the differential equation. Now, before we do that, the first thing is we need to verify if indeed y1 and y2 are actual solutions of this differential equation. So what we do is firstly we say that for y1 equals cos x, we are going to find y prime and then y prime prime, because we have y prime prime here. So we have y1 prime, that is equal to, we differentiate this with respect to x, and then we have negative sin x. Now we have y1 prime prime, we differentiate sin x, we have cos x, and then we have the negative, so negative cos x. Now calling on the differential equation, we have y prime prime, which is negative cos x plus y which is in this case cos x, equals 0. So on the left hand side we have negative cos x plus cos x, and that is equal to 0. On the right hand side you have 0. Now since the left hand side is equal to the right hand side, it means that y1 is a solution to the differential equation. So y1 is a solution to the differential equation. Now let's move on to y2. So for y2 equals sine x, we have y2 prime to be equal to, that becomes cos x, and then we have y2 prime prime. When you differentiate this, you have negative sine x. So also calling on the differential equation, you have y prime prime to be negative sine x plus y, which is sine x, and that is equal to 0. On the left hand side you have 0, on the right hand side you still have 0. So it means that y2 is also a solution, to the differential equation. Now since y1 and y2 are linearly independent and they are solutions to the differential equation, that is the given differential equation, then by the principle of superposition we say that the general solution is given by y equals c1 times y1 plus c2 times y2. So thus we have y equals c1 times, we have y1 to be cos x plus c2, y2 is sine x. So this happens to be the general solution to the given differential equation. And given the boundary or the initial conditions, you can find the values of c1 and c2. Now in the next section we are going to focus on a more easier way in approaching this whole concept, which we call the Wronskian. Now moving on to Wronskian basically describes determinants. So here we have the Wronskian of two functions, which is given by the determinant of a 2 by 2 matrix. We have the first row being occupied by the two functions themselves, and then we have the second row being occupied by their first derivative. Now if you want to find the determinant, you basically multiply f by g prime minus the product of f prime and g. So basically this is how to find the determinant of a 2 by 2 matrix, or basically to find the Wronskian of two functions. Now what happens if we have three functions? Let's say we have f, g, and then h. Now in that case the first row is being occupied by the functions themselves, which are f, g, and then h, and then you have the second row being occupied by their first derivatives, and then you have the third row being occupied by their second derivatives. Now let's try to understand these two cases. So given two functions f of x and then g of x that are differentiable on some interval I, 1, that is case 1, if the Wronskian is not equal to 0 for some x naught in the interval, then the two functions f of x and then g of x are said to be linearly independent on the interval. Now because you are considering a second order linear homogeneous differential equation, if the Wronskian is not equal to 0 and the two functions are linearly independent on the interval, then the two functions f of x and then g of x are said to form the fundamental set of solutions. Now in that case the general solution can be obtained using this formula. Now secondly, in the second case, if f of x and then g of x are linearly dependent on the interval, then we say that the Wronskian is equal to 0 for all x in the interval I. Notice that we did not say that if the Wronskian is equal to 0, it means that f of x and g of x are linearly dependent. We said that if f of x and g of x are linearly dependent on I, then the Wronskian is equal to 0. Now the reason why we say this is it is possible for two linearly independent functions to have a 0 Wronskian. So whenever you have a 0 Wronskian, then it could be that the two functions are linearly dependent or linearly independent. However, if we have much evidence that f of x, the two functions f of x and g of x are linearly dependent, then automatically their Wronskian is equal to 0. So for the given differential equation, what we are going to do is we have the two solutions y1 and then y2. So what we are going to do is we are going to show whether or not these two solutions are linearly independent. And if they are linearly independent, then we are going to find the general solution using Wronskian. So let's try to solve this together. So we have y1 giving us cos x, and we have y2 giving us sin x. Now if this is the case, we want to find the Wronskian. So the Wronskian is equal to, so we have y1, y2, y1 prime, and then y2 prime. So let's try to find y1 prime and then y2 prime. So y1 prime is equal to, we differentiate this, we have negative sin x. Y2 prime, we differentiate this, we have cos x. So to find the Wronskian, we have y1 to be cos x, y2 sin x, y1 prime negative sin x, y2 prime cos x. So we multiply these two values, or these two functions. Cos x times cos x, we have cos square x minus negative sin x times sin x, that becomes negative sin square x, negative sin square x. Now we have the Wronskian to be equal to cos square x, this becomes plus, so plus sin square x, and we know from identities, from trig identities, that this is equal to 1. Therefore, since 1 is not equal to 0, it follows that the two functions y1 and y2 are linearly independent. They are linearly independent, and they form the fundamental sets of solutions for the differential equation, that is y1 and y2. So that by the principle of superposition, we have the general solution given us, or given by y equals c1 times y1 plus c2 times y2. So we have general solution y equals c1 times cos x plus c2 times sin x. This is the general solution of the given differential equation. So now let's move on as we solve one more example on this. So let's try this example together. Given that y1 and y2 are two solutions of a differential equation, y prime prime plus 6y prime plus 8y equals 0, show whether or not y1 and y2 are linearly independent, and determine the particular solution given that y of 0 equals negative 1 and then y prime of 0 equals 8. So we have the two solutions, y1 equals e to the power negative 2x, and we have y2 to be e to the power negative 4x. And then we have the differential equation, y prime prime plus 6y prime plus 8y equals 0. Now the first thing we need to do is to verify if the two solutions are actual solutions of the given differential equation. So we consider y1, so for y1 equals e to the power negative 2x, we have y1 prime, that is equal to, so we are going to find y prime and then y prime prime. Okay, so considering y1, we have y1 prime, that's going to be, we differentiate the exponent with respect to x, we have negative 2, so we multiply that by e to the power negative 2x, and that's to find y prime prime, sorry, to find y1 prime prime, that is equal to, we differentiate this, we have -2, so -2 times -2 becomes +4, and then e to the power -2x. So calling on the differential equation, we have y prime prime, which is 4 e to the power -2x, plus 6 times y prime, which is -2 e to the power -2x, plus 8 times y, which is e to the power -2x, equals 0. Then we try to expand. So we have 4 e to the power -2x. This becomes -12 e to the power -2x, and then we have plus 8 e to the power -2x. So e to the power -2x is common to each of the terms, so we can basically add their constants up. So we have 4 plus 8, which is 12, minus 12, and that is equal to 0. So we have 0 equals 0. So since the left hand side is equal to the right hand side, it means that y1 equals e to the power -2x is a solution. It's a solution to the differential equation given. So let's move on to the next solution, that is for y2 equals e to the power -4x. So we have y2 prime, that is equal to -4 e to the power -4x, and then we have y2 prime prime, that's going to be, so -4 times -4, which is 16 e to the power -4x. So from the differential equation given, we have y prime prime, which is 16 e to the power -4x, plus 6y prime, which is -4 e to the power -4x, plus 8y, which is e to the power -4x, equals 0. So let's expand. So here we have 16 e to the power -4x minus negative here, so 24 e to the power -4x, and then plus 8 e to the power -4x equals 0. So 16 plus 8 is 24, minus 24, so we have 0 equals 0. Since the left hand side is equal to the right hand side, it follows that y2 equals e to the power -4x is also a solution to the differential equation. So it's a solution to the differential equation. So after verifying or after proving that y1 and y2 are actual solutions to the differential equation, the next thing we are going to do is to show whether or not y1 and y2 are linearly independent. So to do that, we are going to find a Wronskian. So let's call this A, and then let's call that B. So we have the Wronskian, and because we are going to find the Wronskian of two functions, we have the determinant of a 2 by 2 matrix. So that is given by, we have the first row occupied by y1, y2, the actual functions, and then second row being occupied by their first derivatives. So we have y1 prime, y2 prime. Let's try to plug in, the expressions or the functions to represent y1, y2, y1 prime, y2 prime. So for y1, we have e to the power -2x, y2 e to the power -4x. y1 prime, we have -2 e to the power -2x. y2 prime, we have -4 e to the power -4x. So we are going to multiply this by that. So here we have -4 e to the power -4x, and then minus 2x. Now since e is common to each of the terms, according to the laws of indices, we can basically add their exponent when the base is the same. So that is that here, minus we want to multiply -2 by this, so we have -2 e to the power -2x minus 4x. So we can have -4 e to the power, this becomes -6x, negative plus 2 e to the power negative 2 minus 4, negative 6, so negative 6x. Now let's simplify. We have common terms in here, so negative 4 plus 2 becomes negative 2, and then e to the power negative 6x. So you realize that the Wronskian is not equal to 0. So since this is not equal to 0, it follows that the two functions y1 and y2 are linearly independent. They are linearly independent. Now, since the two functions are linearly independent, it follows that they form the fundamental set of solutions for the given differential equation. So they form the fundamental set of solutions for the differential equation, that is y1 and y2. So the next thing we are going to do is to use the principle of superposition to find or to obtain the general solution. So to obtain the general solution of this differential equation, let's call that C. So by the principle of superposition, the general solution is given by y equals C1 y1 plus C2 y2. Here we have y1 to be e to the power negative 2x and y2 e to the power negative 4x. So we are just going to do substitution. We have y equals C1 e to the power negative 2x plus C2 e to the power negative 4x. So this is the general solution to the given differential equation. Now we are asked to find the particular solution given the conditions y of 0 equals negative 1, y prime of 0 equals 8. So y of 0 equals negative 1, and y prime of 0 equals 8. So firstly, for y of 0 equals negative 1, we are going to plug in x equals 0, y equals negative 1 in the general solution. So we have negative 1 equals C1 e to the power negative 2 times 0 plus C2 e to the power negative 4 times 0. So negative 1 equals, now e to the power negative 2 times 0 is e to the power 0. Now any non-zero real number or any non-zero value raised to the power 0 is equal to 1. So this becomes C1 plus the same happens to this term, and then we have C2. We call this equation 1. Now for y prime of 0 equals 8, we are going to find the first derivative of the general solution. So y prime is equal to, we have negative 2 C1 e to the power negative 2x, and then minus 4 e to the power minus 4 C2 e to the power negative 4x. Now we know that y prime is equal to 8, so then we have 8 equals negative 2 C1 e to the power negative 2 of 0, that is x equals 0, minus 4 C2 e to the power negative 4 times 0. So we have 8 equals, this goes to 0, so we have negative 2 C1 minus, this also goes to 0, so negative 4 C2. We can divide through by 2 so that we have 4 equals negative C1 minus 2 C2. Let's call this equation 2. Now we are going to solve the two equations simultaneously to obtain the values of C1 and C2. So let's try to add equation 1 and equation 2, because here we have C1 negative C1. So if we add the two equations, C1 goes to 0. So negative 1 plus 4 is equal to 3. So 3 equals C1 plus negative C1 goes to 0. C2 plus negative 2C2 becomes negative C2. So we divide through by negative 1. By negative 1, we have C2 to be equal to negative 3. That is the value of C2. So we are going to put C2 into equation 1. So from equation 1, we have negative 1 equals C1 plus negative 3. We transpose negative 3 to the left hand side. Negative 1 plus 3 equals C1. Now this is equal to, on the left hand side we have 2. So C1 is equal to 2. This is the value for C1. Therefore, the particular solution given the conditions, these two conditions, we have the particular solution y to be equal to C1, which is 2 e to the power negative 2x, and then minus, so we have C2 to be negative 3, so minus 3 e to the power negative 4x. So this happens to be the particular solution of the differential equation given the initial conditions. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.